This is review notes for AP1, chapter 1820, all on a little bit of charge, Coulomb's law, and then on circuits. So there's a lot more to this than what we've learned, but this is what you need to know for the test. So first of all, we have Coulomb's law. So Coulomb's law says that Fe is equal to KQQ over R squared. So it's an inverse square law, just like gravity. And the K on your sheet is given, but K is equal to 9 times 10 to the 9th. It's on your sheet, I think, written as 1 over 4 pi epsilon naught, because epsilon naught becomes important in the next chapter, but that's known as Coulomb's constant. And so it's the same for all charges. Remember, Q's are in coulombs, and you'll lots of times see microcoulombs. Don't forget that that micro means 10 to the negative 6. The charge of an electron is always given to you. It's negative 1.6 times 10 to the negative 19th. That's a 19th coulombs. Of course, a proton's positive. Now, the negative just tells you if it attracts or repels, so don't plug in your signs, just plug in your magnitudes to figure out what it is. So let's look at this one. So you want to always do a free body diagram to determine the direction of the force, because that's what Coulomb's law is telling you. And I want to find the force on Q2. So I'm looking at this guy right here. So I look at number 1, and I'm like, okay, that's a positive force, and so it's going to attract it. So F1 is going to go in that direction, right? And then this one here, down here, that is F3. It's also going to attract it, so it's going to have a force this way, so it's going to have force 2. So that means my net force is going to be pointing in this direction. So if I was adding them up, I would add force 1, and I would add force 2, and then I would end up with my net force, right? The sum of my forces, this is force 1 again, this is force 2, and you would add them up to find the sum of your forces going in that direction. If they're all the same Q, then this would be equal, these two legs would be equal, right, because they're the same distance apart, so this would be equal to whatever KQ squared over R squared times the square root of 2, since it would be a square root of 2 triangle, right? And then you'd figure out what direction it was going based on the triangle. So you should be able to do that. Remember your forces from Newton and all of that, okay? And then here's our vert tables. So this is going more into our circuits. So you need to understand the concepts of voltage, current, resistance, and power. And we just touched upon these. So it's kind of new, but you want to make sure you have the concept. So voltage, energy per charge, not the total energy, is energy per charge. It's what pushes the current. It's like the up part of the hill, unless it push it down. The letter is V. Technically, it's delta V, but we tend to drop it. And then V is equal to IR. That's Ohm's law, right? So that makes sense. Then current is the water flowing, right? So that's the charge per second. It's the flow of the current. The letter is I, and it is Q per T. And then resistance resists the current. So that would be like the rocks in the stream. And so it decreases the current, makes it less, it's R. And then there's lots of equations for R. So R is equal to rho L over A. So think of it like a straw. So the longer the straw, the more the resistance. The bigger the area, the less the resistance. The rho is resistivity. R is, of course, equal to V over I. And R increases with temperature. There is an equation for that, but you just need to understand that for the most part, if something gets hotter, the resistance increases. And then power is energy per time, just like it's always been. So it's how much it costs, it's the flow rate, it's P. There are 3 different equations. P equals IV. Then if you substitute IR for V, you get P equals I squared over R. And if you substitute instead for I, and you substitute V over R, you get V squared over R. So you just have to decide which one to use. So you use these for comparisons. So you look at whatever's the same. So if I'm plugged in the same socket, then I'd want to pick this one, because then my voltage stays the same maybe. It just depends on what you're plugging on. Maybe I'd want to use this one because there I have my V squared over R, and the resistance is different for each one. Remember the units too. This one's volts, and this one's amps, and this one's ohms, and this one's watts, right? But when you're doing your circuits, you want to be able to figure out V, I, R, and P, because once you have two of them, you can pretty much find the other ones that you need. Things to remember for parallel and series is keeping track of which one's which. So parallel is multiple pass, so the resistance goes down because there's more openings, so we can get through faster. So 1 over R is equal to the sum over the 1 over R's. The I splits because of conservation of energy, conservation of charge. I said energy. It's really a conservation of charge because those are particles. And so if whatever goes in has to equal whatever comes out. And the total voltage, which is conservation of energy, is the same because it's in parallel. In series, there's only one path, so the resistance goes up because now they all have to go through the same thing. And the current's the same, and this time the voltage splits. So remember when you're looking at a circuit, so let's look at a parallel circuit. So let's say the circuit goes like this, right? And let's say the current is going in like this. This is a parallel circuit because there's two paths. Okay, so we end up with I1 and I2. So we know that I1 plus I2 has to equal, well, I can call that total. I total, conservation of charge, conservation, the electrons have to be the same as we go through each path. So if I know the resistance of each one, so let's say this is a 2 ohm resistor and a 1 ohm resistor, then I know that more current is going to go through the 1 ohm resistor, right? I know more of it's going to go this way because it has less resistance. But I know it has to add up to the total amount. So I look at, I've got 3 pieces of pie, so 2/3 of the current is going to go this way, and 1/3 of the current is going to go that way. So if I had, let's say, 6 amps, then I would know I2 is equal to 2/3 of 6. And so that would be equal to, I can do my math. 2 times 2 is 4, so that's 4 amps. And then I don't have to do the other one because I know it has to add up to 6. So I can say I1 is equal to 2 amps, right? Now, conversely, let's say we're trying to figure out what the voltage drop is over a series circuit. Because remember, the voltage drop here, right, if I looked at this one, if I wanted to figure out the voltage, it's going to be the same as the total, right, because it's in parallel. So if I know I have 6 amps, and then I can figure out my total, I might as well finish that one, right? So for this guy, let's make a line over here. So for this guy, we know that my total resistance is 1 over 1/2 plus 1 over 1, which is 1/2, which is 3/2, which is 2/3. So my resistance total is 2/3.